Okay, very good. So welcome everybody to the, I believe, 96th Flow Talk. So sorry for not making this into 100, but you have some exciting news that you need to share before you can do the 100. So we're very happy to have you here. Um,
Yeah.
so we have great speaker today, Zach Charles, and a bunch of other speakers. We'll see how you're going to manage this somehow jointly. So welcome everybody, the whole team. Um, so Zach will start this off, as far as I understand, right? And very briefly introduce Zach, he's research scientist at Google working on fairy learning. And before this, he spent some time at Wisconsin Madison. I believe he did a PhD over there, right, in applied math. And he's been doing some really exciting research in the field, and today has some particularly exciting results, as far as I understand, that he's willing to share with us. I'm not going to say much about flow. All of you know what flow is. We just love doing fairy learning and sharing results of the global community in all aspects of fairy learning. So please just take it away. And if anybody wants to ask questions, just ask questions. We'll unmute you, and we'd love to hear your voice rather than read your comments and questions.
Thank you, Peter. And yeah, I just want to say, please ask questions if you have them. We have too much content, so don't wait till the end to get your question answered. So this is going to be a talk that's maybe a little bit different than I think a lot of FL talks that you've seen. This is on federated automatic differentiation, which we will talk about what that is. I should say this is joint work with Keith and Zach Garrett, who are both in the call, and hopefully we'll interject as needed. Yeah, so let's get into it. Motivation. So, the motivation is actually pretty simple. AutoDiff is a really, really powerful tool for building algorithms. You use it every time you train a neural network. And it's pretty obvious that we should be able to use it in federated learning more than just kind of locally doing it on the clients. And so how do we do that? And how do we actually start to make sure that we can do automatic differentiation of federated computations in a way that has privacy and that you can build algorithms that are useful and powerful? Yeah, that's kind of, a lot of different bundles to this motivation. But more generally, I think we are here to talk today to get people interested in this, to say, what can we do with a federated automatic differentiation? We're looking to you all to say, how can we use this tool to kind of make things better? So, so the first thing we have to talk about a little bit is kind of a framing of this work. And I think a theme that comes up over and over in our talk is kind of static versus dynamic programs. Static is kind of programs that you write before you run. So, you use your favorite simulation framework to kind of write a federated averaging implementation. And maybe you say, I'm going to do example weighting. And you say, okay, I've written my program and now it's just going to run statically. Dynamic is different. It depends on kind of runtime values. So instead of doing example weighting, which is kind of fixed a priori, we know what example weighting is. It's you weight the client's update by the number of examples they have. You could say, instead, I'm going to have some kind of parameter which says, given some information from the client, here's how you weight things. Here's how you weight the client's update. So it kind of changes depending on the input that is given at runtime. And so, there's a lot of interesting things in dynamic algorithms. They're generally much more powerful, but static is just easier to talk about. It's easier to write. It's easier to reason about. And so, I think our viewpoint is that a lot of federated algorithms are kind of static needlessly, and that we want to really make it easier to have kind of dynamic federated computations. Keith, if you have some more context you want to add to this.
Oh, just I guess that don't inspect the static dynamic distinction too deeply. It's kind of fuzzy, and it is adaptive optimization static or dynamic? I guess probably dynamic is changing learning rate over time, is that static or dynamic? We kind of lump it in dynamic, even though you can technically like specify the whole path over the course of training when you start. So yeah, it's just kind of a heuristic of the framing, I guess.
Okay, so I think that we would argue that the exploration of FL algorithms has generally been static. There's some fuzziness, as Keith alluded to, but we generally have these pretty well prescribed algorithms when you talk about federated averaging or any of its many variants. There are some notable exceptions. There's some adaptive algorithms that really kind of blur the line, I think. But there's not, I would say, like an easy way to make these dynamic algorithms. Backprop is a really good example of a dynamic algorithm. And it allows people to do all kinds of crazy stuff. You just say, here's my loss function, have at it, backprop, like go do some stuff and build me this cool model. And it's hard to get that same kind of thing working on kind of a federated scale for a couple different reasons. So basically, our goal in kind of the meta theme of this talk is that we want to expand the capacity of federated systems. We want to provide concepts and technologies that allow us to just do more and to create better algorithms and make it easier to express algorithms. And I think a really important part of that is that FL algorithms have a lot of hyperparameters. I mean, just a ton of hyperparameters. Probably anybody here who has done any federated learning research has been frustrated at the number of hyperparameters that they have to tune in their algorithms, right? There's multiple learning rates, there's weighting, there's, how am I going to batch things? How am I going to, whatever. You can talk about any number of like aggregation hyperparameters, privacy hyperparameters, personalization hyperparameters, like they're everywhere. And this is a problem because we don't really know how to set them. Federated learning is much more nascent than centralized machine learning, and we don't really have intuition to rely on. We don't have like too many large scale empirical studies that tell us how to actually set these things, or just a lot of papers to rely on for doing past hyperparameter tuning well. And it's just also more expensive to explore the space of federated learning algorithms, right? It's harder to simulate. It's just more expensive to simulate. You have to simulate all the individual clients. And so basically what we're trying to argue is that this is a larger space, the space of federated algorithms, and it's more difficult to explore. So we really need some kind of tooling to help us explore this space. Yeah. Okay. So, we're going to try to sketch out maybe some reasons you would want some dynamic federated algorithms, and then get into kind of the more technical part of the talk. I think there are two types of algorithms that we're kind of interested in. And these are fuzzy, and there's really not a good way to define these rigorously. But, I think one class of algorithms that we could be interested in are self-tuning algorithms. And this is kind of getting around the problem that hyperparameters are numerous in federated learning and that they're sometimes hard to set, maybe counterintuitive. So you might want algorithms that automatically adjust hyperparameters during training. You could have an algorithm that changes the server optimizer hyperparameters as it runs, or something that changes how it weights client updates as training progresses. Maybe it goes from more example weighting to uniform weighting over time, or something like that. Tuning personalization parameters. We talk about meta learning a lot and its relation to federated learning, and meta learning is learning so that you can do well in kind of like a personalization fine-tuning thing down the line. And you can imagine that you would want to learn hyperparameters that are going to be good for that. Self-learning is I think, a more general class. It's not just like tuning hyperparameters, it's hopefully learning the structure of the algorithm altogether. And you see this, I think, kind of in a lot of model distillation work, where the high-level idea is you have a big model and you distill a small model, but it's not clear how to do that. So you might want to learn how to do that. You might want to have a network that says, give me this big model and I will give you a small model. You could learn kind of any number of things. And one thing that I want to point out in particular is compression. I think learning compression is something that people are really starting to think about. So basically the idea is that instead of statically saying, here's how our algorithm is going to run, let's encode it into a network. Let's learn the network that says, here's how my algorithm is going to run. Because I think experience has taught us that these learned things are oftentimes better than hand-tuned things from people. So that's kind of the very, very high-level view. But how? Even hyperparameter tuning is hard. One point that I want to make here that I think is still true is that a lot of the state-of-the-art self-tuning methods for FL really only tune client hyperparameters, or at least in kind of a structured way. Things like client learning rate. Server learning rate, stuff like that, tends to be done just via random search. Other types of state-of-the-art self-tuning methods rely on hand-computed derivatives. You can differentiate locally to get some kind of derivative of your hyperparameter, or derivative of your model to trick the hyperparameter or whatever. But this is oftentimes kind of error-prone and difficult to test. Or we use repeated runs to figure out optimal hyperparameters. You run a bunch of different trials and you see which one did better. And this is super expensive, and this wastes a lot of intermediate model artifacts. Like maybe you had a model that did okay, its learning rate wasn't like completely optimal, but the model is still useful. It still has useful information encoded in it. Why are we just throwing it away when we try to tune our hyperparameters? Anyways, these are all difficulties of self-tuning, and self-learning is even harder. So really not clear how we do this. Well, kind of the answer that I think the community has repeatedly come to is that automatic differentiation is really a mechanism for doing these learned algorithms. When we have a neural network, we don't say, I'm going to tell you what the neurons are going to look like. I'm not going to tell you what the weights and biases are. We learn it over time. And we just say automatic differentiation, here's my loss function, figure out what network is actually going to do well here. And so this is kind of the high level view of our talk. Is that we want to apply this to the federated learning world, and we want to apply it more generally to the entire federated computation, kind of end to end. And so with that, we're going to talk a little bit about automatic differentiation. We do not assume that you're experts, because we are not experts on this. So this is just going to be a really brief introduction to automatic differentiation. So automatic differentiation is this framework for kind of efficiently computing derivatives of functions who are expressed as computer programs. Also known as differentiable programming. It is not symbolic differentiation. So it's not, knowing the rule that the derivative of ln of x squared over dx, work out some hand derivatives and say, okay, it's 2 over x, And it's not numerical differentiation. It's not, evaluating a function at different points and then reconstructing an estimate of the gradient based on those points. It is a mechanism for exactly computing gradients up to, numerical precision, stuff like that, but of computer programs. And the point, why we use it, it's really accurate. It's efficient. It is expressed as another computer program that can be optimized, and it's less error prone. Anybody who has taught calculus knows that people are very likely to mess up when they're applying the chain rule. This is just a fact of of how humans work. We're not machines. We can't do things completely rigorously, but we're kind of more creative, right? So, anyways, AutoDiff also allows more general programming constructs. You can do things like conditionals, control flow, recursion, and these are all just expressed as parts of the computer program, so it's fine. You can still just differentiate with respect to things. AutoDiff is essentially why I think frameworks like TensorFlow, PyTorch, and JAX have popped off. They allow you to do AutoDiff kind of automatically. You say, here's my loss function, here's the structure of my network, here's my optimizer, and you feed in data, and it just does everything for you. You didn't have to write your implementation of backprop, which is an exercise which I think is useful. And also, I would never trust anybody's, any single person's implementation of backprop more than I could throw it, So basically, AutoDiff allows us to apply gradient descent to virtually anything that can be expressed as certain computer programs. Okay, maybe getting into the weeds of it. How do we actually do AutoDiff? I think a good way to think about automatic differentiation is through this lens of computational graphs. These are directed acyclic graphs representing the computation of a function. So this is a really, really simple computational graph for y equals sine of x1 plus x1 times x2. And I can turn a laser pointer, which is great. So we have our inputs, x1 and x2. We have our output y. And we have these intermediate nodes, which represent kind of elementary operations that are occurring. So v1 is just equal to x1, v2 equals x2. And then we have some very, very elementary things going on. V3 is sine of V1. Sine is kind of one of the elementary building blocks. We know how to apply, derivatives of it. V4 is a product. You can see that by multiple arrows going into it. And V5 is the sum of V3 and V4. Then our output is V5. So this is a really, really simple way to kind of break down this computation to elementary components that are super easy to reason about, right? The most complicated thing that's going on here is sine, and kind of a solved thing since the 1700s. So to compute the derivative of this output with respect to the input, we essentially use the chain rule, and the graph helps codify how we're going to apply the chain rule. So automatic differentiation is really just a programmatic way to compute derivatives via the chain rule as we traverse this graph. So somehow you should think of automatic differentiation and how you do automatic differentiation as being akin to how you traverse this graph. And this graph will tell us how to essentially combine intermediate derivatives via the chain rule. So I think these are maybe some things that people have heard before. I don't know if everybody's familiar with them, but there's kind of two primary modes of automatic differentiation. There's forward mode and there's reverse mode. Forward mode is essentially forward traversal of the graph. So at every node, what we're going to do is compute its derivative with respect to an input. So we're going to compute dv dx. And so, you go through this graph kind of node by node by node. And once you're at the output, you have the derivative of the last node with respect to the input, and therefore you have the derivative that you want. Reverse mode is the opposite. You go backwards. You compute dy dv. And again, if you go backwards correctly and you're computing kind of the derivative of y with respect to all the intermediate nodes, once you get to the input, you're done. You have the derivative that you want. So there's kind of a really important distinction between these, which is forward mode can essentially be done in tandem with the forward pass. So we can compute the derivatives as we compute the function. Reverse mode, also think of backprop in this case, you do it after the forward pass. So you first go through the forward pass, you can compute these intermediate values, and then you go backwards. You use these intermediate values that you stored in order to compute the correct derivatives. So there's an important element here that'll pop up later, which is that, how you are traversing this graph actually affects how you are computing these derivatives and when you are computing these derivatives and what information you need to compute these derivatives. This is a little abstract, so let's just go through a really basic example. Again, for this function, sine of x1 plus x1 times x2, the forward pass is super simple. You start off with kind of just these inputs. You compute the sine of the v1, you multiply v1 and v2, you add v3 and v4, and you get out the outputs of this function. This is our forward pass. And think of this like a neural network if you want. You have your forward pass. Forward mode AD, we're going to start with just computing the derivative with respect to one of the inputs. And so what we do is we have these intermediate things we call d of v. And this is the derivative of any intermediate node with respect to kind of the input. So d of v1 is 1, d of v2 is 0 because they're unrelated. And then we just apply really, really basic calculus and the fact that these are kind of elementary computations that we know how to take the derivatives of to propagate these derivatives. So d of v3, again, v3 was this sine thing, so we know it's going to be cosine of v1. Great. D of v4 by the product rule is going to be d of v1 times v2, and I'm using the fact that the certain derivative is 0. And then you can compute the derivative of the sum, and you get the derivative that you want. Again, it's just like careful application of the chain rule as you go forward. Reverse mode looks a little bit more complicated, and I think to a lot of people it's kind of mysterious the first time you see it. But it's really, really just semantically, we are computing derivatives carefully. And the derivatives that we're computing are the derivatives of the output with respect to an internal node. And I don't really want to go through all of the stuff. You can kind of look at the slide and verify this information is correct, but I'm just applying the chain rule at every stage here. The fact that I know kind of what these elementary operations are and I know how to compute derivatives with respect to them allows me to kind of go backwards and compute this quantity at every node. So one thing that popped up in that example, actually, I should pause here. I think in federated learning world, we're maybe not necessarily experts on automatic differentiation because it's oftentimes just a very, very small building block of kind of general federated learning algorithms. So I want to pause to make sure that kind of this distinction between forward mode and AD and reverse mode AD seems at least clear enough for now to people. Okay, great. So a really important thing that you might have noticed from this example, forward mode, the cost scales with input size. You have to essentially differentiate, do this kind of forward pass thing once for every input, because you have to kind of isolate just computing the derivatives with respect to it. Reverse mode, the cost scales with the output size. So if I want the derivative of y with respect to kind of the inputs, I can actually do it all at once, starting just from the single output. And this is why backpropagation is really useful. Our loss functions are usually scalar, so we can just do backpropagation once and get all the derivatives that we want. Whereas if we were doing forward mode, we would have to do forward mode for every single part of your network, and that's horribly, horribly inefficient. So this is one of the reasons we always talk about reverse mode, automatic differentiation. But forward mode is still like an important concept, and it will be super important for this talk. So now we can get to kind of like actually what this talk is about, which is basically, you know, we had these functions we're taking derivatives with respect to, but let's say f of x is a federated computation, and I'll talk about what that actually means. But just imagine that it's a computation that involves not just elementary mathematical operations, but involves things like communication between a server and clients. The question is then, how do we compute df dx? And I think a really important thing that we want to ensure is that it's still compatible with privacy. You know, f of x might be some quantity that you can compute with sec-ag and differential privacy. And we want to ensure that when we compute the derivative, we are using the same privacy preserving technologies. So again, if computing f is compatible with sec-ag and dp, is computing its derivative still compatible with those technologies? And then the last part of the talk is going to be assuming that we can solve kind of the questions above. What do we actually use this for in the context of federated learning? Okay, pause here. Any challenges to this? Any reason this might seem trivial or useless? Which I think is a totally fair criticism, by the way. I think Keith and I and Zach will be the first ones to say that a lot of this talk is actually trivial. And we'll get to the slide that is the most trivial and I think also most important, weirdly enough.
I totally think if we do our job, then this should be 100% obvious in hindsight. Everything here should be obvious in hindsight.
Yeah. Okay, I got an awesome, so I'm going to proceed. Okay, we're going to talk about this framework, Federated Automatic Differentiation, which we're going to call FAD. This is a picture of a 90s fad. For those of you who remember it, the Beanie Baby craze. We're hoping that FAD is a little bit more long-lived than the Beanie Babies, but you know, hard to argue with the financial success at the time. Okay, so I mentioned this nebulous phrase, federated computation. And so we're going to have kind of a strict definition of what a federated thing is in this talk. Federated values are going to be values with placement. So, you know, we can have a value that lies at the server, and we can have a value that is kind of distributedly lying across all the clients. And these are going to be the only two placements that we consider in this talk, but there could be others. You know, you could say, oh, there's some intermediate aggregation node. That could be a placement. Or you could have, you know, two different classes of clients, clients 1 and clients 2 from different populations, you know. But again, it is just data and also saying where in this federated system it lies. Federated computations are just functions that operate on federated values. So a really important example is federated broadcast. And this is just a broadcast function, right? It takes something that's placed at the server and returns it to placed at the clients. And there's a lot of notation that's being abstracted away here. The clients is usually multiple nodes, but we're kind of thinking of them as a collective. So when we say x at clients, we mean the value x lives at all the clients. So all clients have access to this value x. But you know, generally when we write something like x at clients, it could be different values at each of the different clients. Federated sum is kind of the opposite. It's just summing across clients. So we have something placed at clients, and we then get the sum of it placed at server. This is actually the type system of TensorFlow Federated, which all three of us work on. So it's, of course, an analytic tool that we think about. But I think we really do believe that this is a useful way of thinking about federated computations. I think when you're writing an algorithm, it's very easy to get unclear about where something lies. And the problem is that this is actually incredibly important in federated learning, right? You want to make sure that, node X does not have information about node Y. And in terms of the differential privacy in SecAg, you want to actually make that even more formal. So this is kind of a useful framing device, I think, throughout. So we had computational graphs for automatic differentiation. And so what we're going to do is just define a federated analog of them. So again, computational graphs were these graphs where you had values and kind of the arrows represented intermediate operations. And we're going to do the same thing, but where the nodes represent federated values. So basically, every node represents a value and a placement. And this is a really, really simple example. We have some input X. We just say, okay, V1 is now our internal node that's set to X. We apply some function on the server that does some kind of transformation of it. We federated broadcast it to all the clients. All the clients have some local data ZI that they then combine with the thing that they received to get some output. You take a sum of all those, you do some transformation, and that's your output. And if you stare at this for long enough, you might realize that this is actually representing federated averaging, or that federated averaging can be represented through this diagram. X is your model. You maybe want to do some kind of intermediate processing on it. Maybe you want to compress it. I don't know. You broadcast it to all the clients. All the clients have their local data sets that they aren't going to share. They combine the model and the data set to get some update to the model. The server sums up all those updates. Really, it takes an average, but you can represent an average as taking a sum of two different quantities and then doing some division post-processing. So that's kind of what this F3 is representing. And then you get your updated model. And kind of the point here is that every single arrow is representing a pretty simple operation that mostly we know how to take the derivatives of. There are kind of a couple problems, though. When we want to compute dy dx, so the derivative of the output with respect to the input, we have these federated things that are happening in between that I think we should pause on. They're pretty simple operations, but they're really, really critical when you start thinking about privacy preserving technologies. So as kind of a rudimentary answer to how we compute dy dx, we can do the following really stupid operation. All the clients send all their data to the server. The server then recreates this computation in full, entirely locally within the server, and it could just apply autodiff. And 100%, this allows you to compute the derivative of the output with respect to the input. And also 100%, this is not privacy preserving. This is a really bad algorithm for computing dy dx in a privacy preserving fashion. So if you start to think about what are the actual obstacles to preserving privacy while computing this derivative, I think it immediately starts to become clear that the key is what do we do with the communication boundaries. One thing that's really important is, when you're doing differential privacy, the way differential privacy works is that it's injected in kind of at the aggregation phase. You add this noise and you clip, and that allows you to have the kind of this plausible deniability. It's also important that for things like differential privacy that we use a broadcast where everybody gets the same model. If you gave everybody a different model, you might be able to, down the line, extract, hey, I know what this person's update because I gave them this fake model that I can reason about. So we have to be careful when we do kind of automatic differentiation across communication boundaries. This is the slide that I said was trivial. It absolutely is. These are the simplest observations you could possibly make, and they're also really important. The first, moving a value around does not change its derivative. So the federated broadcast of a derivative is the derivative of a federated broadcast. This is a really, really trivial observation. I can basically, if I want to compute the broadcast of a derivative, I can just broadcast the value, and then locally at each client, take the derivative of that value with respect to a thing. The second is something that everybody has known for years, or maybe you just learned it, whatever. It's a trivial fact. It's that derivatives can be the sums. So the federated sum of derivative is the derivative of federated sum. It's a really stupid observation. But what it implies is that essentially we can just apply forward mode automatic differentiation by augmenting our federated broadcasts and our federated sums and then just kind of applying automatic differentiation everywhere else. This is forward mode federated automatic differentiation. And what we're going to get to an explicit example of it. But I'm going to pause because I think this is such a trivial slide that it's worth pausing on. Keith, I don't know if you had something you wanted to say about this.
Oh yeah, one comment that I guess is important to make is that all of the differentiation primitives that we use in this work are kind of assuming like derivative with respect to singleton. So we make no attempt to differentiate with respect to like client's placed value. In which case you would see probably 2, for example, would break, because it probably should be a, you know, if I sum up a bunch of things and I want to differentiate with respect to that, the summation argument as like a singleton, I probably should have just a vector of 1s basically. That would be like a client's placed 1 here. So yeah, that's one subtlety that I think it was not obvious to us when we started thinking about these things.
Yeah, it is really important that the derivatives we're talking about inputs and outputs that are placed at the server. Once you start having inputs and outputs placed at the clients, things get hairier. So let's actually start, saying what we mean by these augmentations. This is essentially the forward pass of our algorithm that we kind of talked about before. Again, very simple. You receive this input V1, you compute some V2, you send it to all the clients via federated broadcast. The clients receive this federated broadcast thing. Clients compute some V4 based on their own local data and what they broadcast. The server gets the sum of those things. The server computes some post-processing on that value, and then it sends it as output. And if I want to do forward mode FAD, what I do is I just augment all of these steps. So I again receive the same input, but now what the server is going to compute is V2 and V2 dot. And V2 dot is going to represent the derivative of V2 with respect to X. So anytime you see a dot here, it is the derivative of that quantity with respect to the input. The server can compute this just using standard AD, right? These are all values placed at the server, so they can apply, their favorite PyTorch or JAX or TensorFlow operation and compute V2 dot. So then clients are going to receive V3 and V3 dot, and this is where that observation that we talked about came into play. V3 dot is just federated broadcast of V2 dot. So we're just adding an extra thing into our broadcast. We're saying, okay, we're going to push forward both V2 and its derivative. Then clients can compute V4 and V4 dot just using standard automatic differentiation frameworks. Locally, they can apply PyTorch or JAX or whatever. And then we do the same thing with the sum, just in reverse, where V5 dot is going to be the federated sum of V4 dot. And then you can kind of compute everything that you want. The point is that anytime we're actually taking a derivative here, we're using local AD, but all of our communication is going to be augmented with kind of extra communication that's going to allow us to propagate these derivatives. And the other really important thing about this is that all we've done is augment a broadcast with another broadcast and a sum with another sum. And the point is that this actually preserves compatibility with things like differential privacy and SecAg. Generally, things like differential privacy and SecAg require that communication from server to clients has to be broadcast, and communication from clients to server has to be sum-based. This is not entirely true, but it's like mainly true. And so we took one federated algorithm, we transformed it into another one that involves still the same communication primitives, and therefore it still has the same compatibility with privacy preserving technologies. The original one was DP-able, the next one is also DP-able, which is a really important, and it's part of why we focused on this kind of maybe strange framework, is that it allows us to preserve compatibility with these things. Okay, pausing here. Oh, sorry. Yeah. Okay. I should have said what SecAg and differential privacy are. So DP stands for differential privacy. It's a mechanism by which you can say that the output of a computation did not rely on any data within the computation. It allows you to say that mathematically the output of some function does not leak information about kind of data that clients have. SecAg is different. It's a cryptographic primitive, instead of kind of an information theoretic one, but it allows you to essentially take sums without having to send intermediate values to the server. So the server never actually receives kind of individual values of like the V4. It just sees the sum, and it cannot, cryptographically speaking, cannot reason about what any individual update was from client. So these are privacy preserving technologies. Essentially, they're ways to say that, you know, under some assumptions, our algorithm does not leak data about any of the clients. Yeah, very good question.
Okay, thank you. So like in DP, for example, we add noise or something, but SEC AGG, as you said, it's something about in aggregation step, the communication won't allow individual communication. Is that right?
Exactly. So kind of the standard way to do differential privacy is a Gaussian mechanism. You generally clip and then you add noise. SecAg is different. It essentially what you do is you want to take a sum of values across clients, and what each client will do will be to add and subtract values in a very prescribed way so that all the additions and subtractions cancel out, but so that the server can't tell what value actually corresponded to any given client. You just see essentially things that look kind of arbitrary, but when you sum them up, you get the true sum. So, and it's, you know, it relies on cryptographic hardness, which is kind of its own topic that I'm not an expert in, but yeah.
Thank you very much.
Yeah. Okay. There are some downsides to this forward mode AD. You know, one of the things that is a problem with forward mode AD locally in kind of machine learning is that the cost scales with the input size, which for neural networks is really, really big. And the same is true of forward mode FAD. The computation and communication costs now scale with the input size, which is really bad, right? Like if you're sending a 3 million parameter model, now you're having to do forward mode a bunch of different times because it has to scale with the input size of your model. However, it doesn't require resampling clients, which is just keep that in the back of your head. You know, all we had to do was transform our computation. We didn't have to run our computation multiple times. We didn't have to query the same set of clients multiple times. We could just kind of sample some set of clients, tell them to do something, and everything worked out. And one thing that's really important, you know, this communication cost scales with the input size, but if we're just doing derivative with respect to hyperparameters, that's not such a big deal. You know, if I'm adding the derivative of some learning rate here, that's just an extra scalar. That's not really such a big deal. So, but still, we would like to know, how do we make this more scalable? And kind of the answer that already exists in literature is reverse mode, since it scales with the output size. We have some less simple observations, which are kind of the same analogs as the trivial ones that we made before, but they look a little bit different because you have to flip the numerator and the denominator. But basically, what we can say is that if y is a federated sum, then the derivative of z with respect to x is the federated broadcast of derivative of z with respect to derivative of y. You can tease that out if you want, but what it means basically is that if I want to do a reverse mode kind of operation, a sum is going to turn into a broadcast. And similarly, broadcasts are going to turn into sums. And you can track through the chain rule application here. But basically what it means is that if we want to do a reverse mode FAD, we do a forward pass through our computation. We store all the intermediate results on the clients, and then we go backwards. And when we go backwards, anytime that we encountered a sum, we turn it into a broadcast. Anytime we encounter a broadcast, we turn it into a sum. And this gives us reverse mode FAD. So this is kind of the pseudocode of it. This is the same forward pass as before. And once we're done with this forward pass, we go backwards. And basically the point is that when we had a federated sum here, that turns into a federated broadcast. And then when we had a broadcast over here, that turns into a federated sum. And the really crucial thing here, again, we were saying that broadcast and sum allowed us to have compatibility with things like differential privacy and SecAg, and this is still true. We had something that had broadcast and sum, and we get something that has broadcast and sum. The order is different, but it's still the same. And it also scales with output size, not input size, you know, just like reverse mode AD does. The problem is that it requires 2 rounds of communication. And those 2 rounds of communication actually have to involve the same set of clients. And this is really bad. Querying clients multiple times involves all kinds of synchronization, which is expensive. And it might just be really, really difficult. Clients can drop out of federated computations, and that'll make this kind of not easy to do. In cross silo, this is fine. Like this is just going to work out. You know, if you have just a couple clients and they're always participating, this is actually going to work great, but not necessarily in cross device. So I think I only have 15 minutes left, so I'm not going to go into it too much, but basically say that we actually have a compromise that allows us to avoid this multiple rounds of communication while still preserving some of the good qualities of reverse mode FAD. And that's something we call mixed mode FAD. And I think at a high level, what it is, we apply forward mode to kind of the communication primitives, and locally on the server or locally on the clients, we apply reverse mode. So, you know, locally the server is going to use reverse mode 80 and the clients are going to use reverse mode 80. But, you know, in terms of the communication primitives, we kind of apply a forward pass. And so what this means effectively is that we're communicating Jacobians, and we have to multiply them correctly in order to kind of do our forward pass. But it again preserves the fact that we're just using federated broadcast and federated sum, and it doesn't require multiple rounds of communication. So it you know, it has some trade-offs as well that I don't think we have the time to really get into, but it's a probably good compromise between kind of forward mode FAD and reverse mode FAD. And so yeah, like I was saying, it scales with the output size, not the input size. There's multiple inputs and outputs at different stages of this, so you have to take that with a little bit of a qualifier, but it does only require one communication round. Kind of the big downside of mixed mode FAD is that it potentially involves large matrix multiplications of the server. So that is kind of its downside. I don't think there's no free lunch. None of these are going to be perfect, and I don't think there is a perfect FAD algorithm, but yeah.
Super elucidating, because, you know, again, like you see the factors, you know exactly what the algorithm is doing. So I think designing adversarial data would be quite simple, but then, you know, to look back inside the box and say, okay, why did they give the label? Well, because you designed it that way. So I'm not, yeah. So, but I think in terms of like, okay, how does it handle that robustness is an interesting question that I haven't seen a whole lot of.
Thank you.
Wait, is that about? I think this is a different talk.
Please feel free to put a question in the chat if you don't want to unmute.
Yeah, okay. I don't know if somebody can mute them. I'm going to proceed. Interesting. I think they're listening to multiple talks, which is fascinating to me. Okay. So let's get into applications with kind of the last 10 minutes. So we focused on applying this FAD to the FedOp framework, which includes things like FedAtom, FedAverage, Fed SGDM. And basically, we wanted to use it to tune hyperparameters using backpropagation, essentially. This gives you an algorithm called hypergradient descent, which I think has really, really exploded in popularity over the last year. There are some really notable papers applying it. And it basically, you just apply gradient descent to the hyperparameter. So you differentiate the loss with respect to the hyperparameter so you can apply gradient descent. And so we use FAD to do that on federated algorithms. The problem is that you need the derivative of the loss with respect to the hyperparameters. The hyperparameters are generally at the server. So the way we solve this is we use FAD. FAD allows us to essentially take derivatives of anything with respect to anything, as long as they're server placed. And so maybe just to get into a little bit, FedOpt has this kind of rough framework that basically mirrors what we were seeing before. And this gives us some model that we update kind of at every round, kind of like in federated averaging. And basically, we want to apply hypergradient descent on the clients. That's easy, right? You can apply hypergradient descent locally and just use standard AD and everything works out. But if you want to do it at the server, you have to use FAD, generally speaking. And maybe just to make this a little bit clearer, we have this hyperparameter at the server, and we want to compute the derivative of the loss with respect to the hyperparameter. And to do that, we need to expose some loss on the server that we can actually differentiate through. And so what we do is we have kind of the first half of our algorithm just is basically federated averaging. And then we augment it with this extra step, this kind of federated evaluation that gives us a loss function or a loss value on the server. And now that we have this kind of whole thing end to end, we see, okay, the server has an average loss here and has a hyperparameter here, and I can just apply FAD using any of the three modes that we had before, and it allows us to get a derivative of the loss with respect to the hyperparameter. So again, it did require augmenting our computation with an extra round of kind of evaluation. The good thing is that you can do this in parallel. You can do kind of loss computation while you do the model update, and you apply FAD and you just get the ability to essentially self-tune any hyperparameter using hypergradient descent. That's kind of the high level structure. And maybe just to skip to some of the results, we applied it to 2 different things. The first thing we applied it to was client weighting. So FedOpt and federated averaging and algorithms like that, they involve a weighted average of client model updates. And so kind of one example is example weighting, where you weight things by the number of examples on client. Another example is uniform weighting, where it's kind of just everybody's weight is 1. And there's kind of interpolation you could do where the weight is the number of examples to some power, where let's say that Q is a hyperparameter. So we used mixed mode FAD to actually self-tune this parameter Q throughout training. We did this on a couple baseline tasks, but the thing I want to maybe mention is that actually on a lot of tasks, it did nothing. It did as well as example weighting, but example weighting was also doing as well as uniform weighting. So these tasks weren't heterogeneous enough. They were actually weirdly homogeneous, and that included the Stack Overflow task. So instead, we backtracked to actually a synthetic logistic regression task from the FedProx paper. It was not designed for kind of self-tuned client weightings, but it was actually a benchmark for heterogeneity-aware FL methods, and so that's what we used it for. And this is a plot of essentially what happened when we compared uniform weighting, example weighting, and this kind of learned weighting for different initializations. So in the first plot, we initialized at example weighting. And what we can see is that this learned weighting did really, really comparably to example weighting. And then at the end, uniform weighting suddenly does better. This is just a feature of the data and the tasks. And it actually is able to adapt. So it starts off with kind of this exponent of 1, it increases, and then over time it decreases. It realized, hey, uniform weighting actually ends up being better. So we can actually learn that this hyperparameter should change. And you see similar results when you initialize at Q = 0. You know, it does worse than example weighting for a little bit because it was initialized at kind of the wrong thing, but it learns that. It compensates, and then it goes back down when it realizes, no, wait, I need to switch to uniform weighting. So this was really, really validating. It was suggesting that this thing is actually doing what we want. It's saying that initially I should be example weighting, and then later on I should be uniform weighting. We also applied FAD to server optimizer hyperparameters. And specifically, people might know, a really, really common way to do federated averaging is to also include an optimizer step on the server, where you use things like SGD with momentum. And so that'll have a learning rate and a momentum value. And so we basically applied FAD to the same kind of, in the same way as before, we applied it to these server optimizer hyperparameters. And I think this is kind of the most interesting application that we had. Maybe just some background before we get into the plots. We ran experiments across 5 really, really common benchmark tasks. And remember that this is hypergradient descent. So there is actually this outer optimizer that is doing gradient updates with respect to the hyperparameters. We basically didn't tune it because we wanted to show that this method was kind of more robust. We did like a couple initial trials that on just a single task that said that a outer learning rate of 0.01 worked pretty well. And we just reuse that everywhere else. And so what we did is we essentially compared it against random initialization of learning rate and momentum. So kind of learned versus random search. And the learn just was better. It got to better accuracy ratings, and it did so faster, kind of in less total computation time. And so learning rate did not help in some degenerate cases, but generally was really, really successful. And maybe just to plot things, basically we ran multiple trials, with both learned and kind of fixed but random learning rates. And this is kind of essentially what accuracy you get after how many trials. So ideally, we want to run as few trials as possible. We just want this thing to be good out of the box. And we kind of see that. We see that, if we run 10 trials, we do really, really well. Whereas, if we do kind of a random search of learning rate and momentum values, it takes a really, really high number of trials before you actually get good performance. This is true on Stack Overflow. This is true on Shakespeare. EMNIST is the one where it wasn't necessarily true, but EMNIST is just a really easy task. all of the learning rates and all the momentums worked pretty well. So everything just did kind of comparably. And then we saw in Stack Overflow kind of a tag prediction task in Cypher 100. Again, the learned hypergradient descent type approach enabled by FAD was just much better and achieves much better accuracy much quicker. And so the idea here is, yes, we introduced this new hyperparameter that is kind of the hypergradient learning rate, but it didn't really matter. It still made it much, much easier to actually tune our tasks because we didn't have to play around with all kinds of random initialization of everything. We could just learn them. Okay, I'm gonna pause here. Okay, I know I only have a couple minutes. Oh, please.
Yeah, I get a question. This is a way back to your earlier. You lost me at the part of what's the derivative become a sum different derivative. That part I was a little confused, and that I thought that's a key of your auto differentiation algorithm. So that maybe you can explain a little bit on there one.
Yeah. So this is just you can see our paper for more details. Same title. It's just an application of the chain rule. And it's basically, I think the thing to have in your mind is the idea that a derivative of a sum is the sum of a derivative. So when you're computing these derivatives kind of throughout your federated computation graph, anytime in the forward pass that you would have seen a sum, you now get another sum of the derivative. It just allows you to reason about how you go from a sum of a value to a sum of a derivative and kind of vice versa.
Okay. Got it.
Yeah, but yeah, it's hard to give all the details right here. Yeah. Okay, just kind of moving forward. This is an example of some of the trajectories of our learned parameters in some of these cases. This is on the Stack Overflow task. We see some pretty interesting stuff. It learns to initially set the learning rate really high, kind of like warm up, and then cool down eventually. And it actually does a similar thing for momentum. But on a different task, it actually says, no. My initial learning rate was way too high. I just need to decay throughout the task. So it's really kind of adaptive to its initialization, which is a really nice feature. I only have a couple minutes. I just want to talk about some future work. This is kind of a proof of concept more than anything else. But the first thing is really developing a practical FAD system. You know, we have practical AD systems like PyTorch and JAX and TensorFlow. And we really want it to be kind of a future work to get FAD implemented in kind of full generality and make it easy to use. This is not completely trivial. This is pretty actually difficult. There's a lot of bookkeeping necessary for these federated chain rules that we've been talking about, and you really have to carefully handle things. And we'd also like to extend to differentiation of client place values and move beyond just like broadcasts and sums. You know, you can move beyond them, but then there's a complicated privacy story, which we have to kind of dissect more. We're interested in other applications of FAD. You can do things like maybe interpolate between federated averaging and FedSGD. This is something that people have already started to do in the literature, and it's really, really effective. It helps mitigate kind of the client drift issue that pops up in federated averaging. We're really interested in it for personalization. You know, hopefully it can allow us to actually learn personalization algorithms that are better. We want to apply it to kind of learning systems. You can imagine things like a compression method that actually learns how it's going to compress the updates over time, which would be really, really nice from a communication perspective. And the last thing is kind of learn modularity. You know, we have these very, very large models that we're thinking about, and you can't broadcast like a billion parameter model to a client phone. So what you would like is something that kind of distills the model and learns how to distill the model throughout the training process. And one area that we're looking at right now is kind of, well, what about sparse mixture of vectors models for federated learning? So, you know, this is kind of a whirlwind of the things that we're interested in, but we're really interested in hearing what people have to say and people's ideas of what might be use cases for federated autodiff. So yeah, if you have any thoughts, you know, please reach out. I think we probably have time for maybe one question.
So we have more time because it's okay for people to leave and those who have more time to hang out. So don't worry about this. Yeah. So maybe I have one question. So just like when we come up with some federated learning algorithms, and want to compare this to centralized algorithms, how much do we lose? My question would be, how much would you lose when you compare to centralized autodiff? Do you lose at all or nothing? So I'm trying to remove the federated computation out of this and only thinking about the federated automatic differentiation.
I think to me the moral that pops up is that for centralized autodiff, the only thing you really have to worry about is how much computation you have to do. For federated autodiff, you also have to worry about communication. Anything that increased computation in centralized AD probably also increases communication in federated AD. So I really think that's where we're losing out. And you can try to compensate for that communication increase by doing matrix multiplications and all that, but it's like a fundamental barrier that I don't think can be circumvented.
Right, but am I correct that in your plots, these two things were put together? So we couldn't disentangle the effect of the federated computation and the FET, right? This was all combined together. I mean, I would love to see just the effect of one in order to see how efficient that FET is on its own without the baggage of the federated computation.
This is a good question. I don't think I know exactly what the right centralized benchmark would be. I
don't know that either, but I just thought that having an answer to that might be interesting.
Yeah, I think this is a really good point.
It'd be almost pretending that you have all the data centralized, right?
Yeah.
Doing the whatever training there, but then replicating the autodiff in a federative way and using those values to adjust the hyperparameters, right? And see how much do you lose compared to actually doing centralized autodiff, right?
Yeah, I think this is a really good point. And actually, this is a good use case of that bad algorithm I was mentioning, which is send all the data to the server and then update there. Yeah, I think this is a really good point. This is something I would love to look into. And I do agree that getting better comparisons to like what is the efficiency loss with respect to centralized, like that's true of this paper, and I think of a lot of FL work. Like that's
and the reason why I'm asking because there's a lot of work on automatic differentiation on centralized, right? So, and we would want to see, or you would want to see, I guess, how much of the gap you can close.
Yeah, and I do think there's a bit where we probably need better software for it first, that is like actually optimized, and then we can start to really make those comparisons in I think fair ways. And yeah, very big proponent of that idea. Thank you.
Okay, so here's a question by Yegor. I unmuted you. Go ahead.
Hi. Yeah, thanks for the brilliant talk. I was curious about the like optimizer that you used for adjusting the hyperparameters. Did you like try different options and like how sensitive it was to the choice of this optimizer?
It's a good question. We did experiments that had both SGD as the kind of outer optimizer as well as Atom. And I think we saw almost no difference. Keith, can you correct me on that? I don't remember seeing any distinction, and it was pretty robust to initialization.
I think that we definitely didn't do like extensive comparisons on the outer optimizer. And I think it's important to note that we like really didn't tune it at all. Just kind of like picked something that seemed to work okay in one instance, and we're like, hey, yeah, just throw this at everybody else. I think in general, it's definitely will not work. I think that this kind of relied on the fact that probably there's only a single, or I guess there's two parameters that are being adjusted here, and like they're probably roughly at the same scale. So you didn't need any kind of like adaptivity to deal with that fact. But I also think that like, that the experiments that we actually did, we totally think of them as like purely illustrative, just like, this actually might be something you would want to do. Definitely in no way like optimized or explored well. Yeah,
got it. Thank you. And if I may, I would like to ask another question. Yeah, I was also curious, like whether you explored like the intersection of this idea with differential privacy in practice, like how like this kind of additional noise may affect the like optimization process, in the sense that, like, if we consider FedOpt as some sort of HGG type method, then like injecting that additional noise in some cases may not affect it that much. Like HGG can be kind of robust to that, but I don't have like a good intuition regarding this hyper gradient method. Yeah, did you encounter anything like this in the like previous literature, or maybe you can share your intuition?
So we didn't. What I will mention that this is something that we have as a potential follow-up. If you, Zach, if you go to the plot that has the learning rate trajectories on it, yeah, this plot on the left-hand side here, that was actually initialized to learning rate of 1.0 and momentum of 0.9. And it initially started by going down and then going back up, which was like a weird coincidence with something that a few of us observed in like a different work stream, that this particular task, like, it's kind of like a, whatever, it's like an edge of criticality thing. It's like, this was like the well-tuned version is like 1.0 learning rate and 0.9 momentum. But it causes like half of your runs to diverge or something like that, but it will achieve the best like accuracy for you if you just look at your maximum. This procedure here on the left actually like dramatically increased the stability of that. None of our 50 runs diverged from the same initialization here, whereas about half of the other ones did. And that was essentially observed in a different work stream in the context of doing DP optimization. Like, oh, if we do some like arbitrary clip of the updates we get, we can kind of like dramatically stabilize this training. So there is an interesting question: can you marry those two things to like really benefit for you and not have to like, you know, mess around with setting some like this crazy clip hyperparameter? But we've never followed up on it.
And I would add to that, I don't think that I'm not aware of any work that does hypergradient descent with differential privacy. I think it's a really interesting and unexplored landscape. Because yeah, I think intuitively you could imagine that noises might destroy structure of hyperparameters, and it's really something that needs to be analyzed more systematically.
Mm-hmm. Yeah, thank you very much, and thanks again for the great talk.
So on the slide, you learning both of these parameters jointly, right? It's not separate. Okay. And what is the most you've learned at the same time?
I guess I think some of our learned optimizers, we experimented with parameterizations that were higher dimensional.
More than,
but we never went very far, probably up to like 10 or so.
Okay.
Yeah, it's worth noting, this hyperparameter Q that we're learning, we're eliding some details here. This is actually the output of some like 5-dimensional computation that has to do with the stuff on the client, like how many examples they have and their loss value. But yeah, we didn't go beyond 5-dimensional.
So what I would be interested in, this is just my own Gedanken experiment. So let's say that you learn just 1 or 2 hyperparameters, some very low dimensional. And instead of doing any of this autodiff, just taking some sort of a little low dimensional hypercube or something and randomly picking points in each communication round and trying to just do this in a derivative-free fashion. Right? And I'm wondering that we got a good baseline to compare to, because it's a very stupid baseline, right? Not trying to use any gradients or anything, kind of doing random search, but still changing things a little bit and trying to learn from that. From that. And I would want to see whether this overhead of this fat has an extra benefit on top of this, and I assume it would. But I'd like to see how much.
Yeah, 100%. And I think to add to that, you know, a more sophisticated baseline that is in the same vein is kind of these Bayesian optimization methods.
Right.
And yeah, absolutely. I think this is like the next baseline that we absolutely need to showcase. I think intuitively, there's a lot of benefit from kind of keeping around model knowledge that you know while learning these other hyperparameters and not just throwing it out. But yes, this does not conclusively demonstrate that yet.
Any other questions by anyone? I like waiting for more time than others deem appropriate for questions. Because I have the hypothesis that people like to think about what to ask.
I used to do this when I TA'd calculus. I would tell my students, I'm getting paid for this time and you aren't. So, you know, let that sit with you.
Yeah, but while people are thinking, I thought it was a great talk. Thanks a lot for putting it together and for jointly presenting this. It's fresh air. It's a kind of new thing. So congratulations, and hopefully this will have some traction. And I'm sure internally already has, right?
Yeah, I think that we know what we need now primarily is like software to make this actually easy to use, because it is really not. Like we did hand implementations of everything.
Yes.
Yeah.
And unfortunately, it could be that we develop that software and then realize, oh, this is now useless. But until we actually have like optimized implementations of it, it's actually hard to say.
Yeah.
We are very encouraged, though. We think this is actually going to be very useful.
I think it's a good idea. Yeah.
Well, thank you for having us. We really meant it when we said that this is kind of new and also trivial. And so we're really looking for kind of where is this going? What should it actually be applied to? And we really don't have a lot of ideas, or at least what we mean to say. We have tons of ideas. We have too many ideas, and we would love validation to see what people are interested in, what people are trying to accomplish. So please reach out if you have questions or thoughts or comments or criticisms, really, anything. Yeah, we'd love feedback.
Yeah, well, thanks a lot. Great having you, and thanks everybody for attending.